Dear students, today we'll learn about the optimal binary search tree. An optimal binary search tree is one of the very important feature of a data structure. Before getting in detail about the optimal binary search tree, let us now discuss about the binary search tree. A binary search tree is nothing but it is an ordered set of key elements which is used to perform the search, insertion and deletion operation. The keys that are most frequently used are present nearer to the root, and the one which is less frequently used are placed far away from the root. This is what is the arrangement of a binary search tree. Now, in order to proceed with the binary search tree, we have certain assumptions which is nothing but k is equal to k1, k2 up to kn, which is the number of keys that is present in a sorted order, and P of I and Q of I represents the probability of the successful and unsuccessful search. We have some notations in order to solve the problem. Tij represents the optimal binary search tree, Cij represents the cost of the tree, and Wij represents the weight of the tree. Rij represents the root of the tree. Now, in order to identify the difference between the probability of successful and unsuccessful search, probability of a successful search depicts like, suppose in order to find out the element 35, which is like the arrangement is the element which has a value greater than the root or present in the left side, and the value lesser than the root or present in the right side. Since 35 is greater than the root, I search for a one down search in the left side and I found out the element 35 here. For an unsuccessful search, suppose if I need to find out the element 5, I'm checking for the root, and since it is 30, the lesser value obviously presents in the right side and it goes for 10, and we don't have the element 5 here, so this is going to be the unsuccessful search. We have 5 different combinations of unsuccessful search, which is nothing but we have 2 different combinations here. If the key is found, P is incremented. If the key is not found, Q is incremented. To understand the concept more clearly, let us now discuss with the help of a problem. In order to solve the problem, we have to find out 3 different things. The first one would be the cost, and the second one would be the weight, and third one is the root. For finding out the cost, we have the formula C of I, k minus 1 plus C of k, j and W of I, j, where we are supposed to find out the minimum using the k value and then obtain the optimal binary search tree. Consider the question. We have 4 elements A1, A2, A3 and A4. Do, if, int and while. The probability for the successful and the unsuccessful search are given as P and Q values. Now, in order to start with the problem, the initial stage is j minus I is equal to 0, which will lead to a combination of 0, 0, that is I and j both remains the same. That is j minus I is equal to 0 will be like 0, 0, 1, 1, 2, 2 and 3, 3 and 4, 4. So it is like W of I, I will have Qi, and the cost of I, I will be 0 and the root of I, I will be 0. This is what is the first combination, and we'll have 5 different combinations here. And using this formula W of I, I is equal to Qi, we would find out the 5 different combination value. Qi represents the probability of the unsuccessful search that is given in the question. Q0, Q1, Q2, Q3 and Q4. Now, the step 2 would be j minus I is equal to 1. J minus I is equal to 1 will have 4 different combinations: 0, 1, 1, 2, 2, 3 and 3, 4. Now, in order to compute the weight, we have the standard formula Pj plus Qj plus W of I, j minus 1. We will find out the weight for all the 4 different combination and keep it aside. So for w of 0, 1, p of 1 plus q of 1 plus w of 0, 0. Since we have j value as 1 and 1 minus 1 will be 0 here. W of 0, 0 we have already obtained in the previous stage, which is nothing but 2. P of 1 and Q of 1 are the probabilities that is given in the question already. So using this, we have computed the weight for 0, 1, 1, 2 and 2, 3 values. Now, the next stage would be computing the cost for these 4 combinations. In order to obtain the remaining cost values, we would use the formula minimum of C of I, k minus 1, C of k, j and W of I, j. Here we have 4 different combinations and the k values we are supposed to iterate in such a way that it starts after 0 and ends with 1. See the limit from I to j and the k value is in the mid. The value before the k will be k minus 1. We have a combination of I to k minus 1 and k to j. This is what is the combination we have obtained. So in order to proceed with this problem, since we have only one different value, so k is equal to 1 and we have obtained the r value directly as 1. The next stage would be j minus I is equal to 2. We have 3 different combinations for this: 0, 2, 1, 3 and 2, 4. The combination of cost value differs only at this particular stage, where we have the k values to be iterated after 0 till 2. We have 2 different k values, k is equal to 1 and k is equal to 2 at this particular stage. If at all we proceed with the problem as k is equal to 1, the minimum value that obtained at this particular stage is 7 plus 12, which is 19, and if we proceed with k is equal to 2, then we have 8 plus 12 is equal to 20. So the minimum among these two values is 19 and the root will be 1. That is, the search is minimum when we have k value as 1. Computation. To proceed with the next computation, j minus I is equal to 2. We have 3 different combinations: 0, 2, 1, 3 and 2, 4. We would obtain the weight for all these 3 combinations using the formula P of j plus Q of j plus W of I, j. In order to obtain the cost, it slightly differs only at this particular stage, where the k values are iterated after 0 till 2. So we have 2 different combinations, and out of the 2, the one which has the minimum value is taken as the root node. Using the same procedure, we have computed the cost value for C of 1, 3 with the iteration k is equal to 2 and k is equal to 3. Same way, we have computed the iteration for C of 2, 4 using k is equal to 3 and k is equal to 4. Now, the next task is we need to find out for the combination j minus I is equal to 3, where the combination of the I and the j values would be 0, 3 and 1, 4. We have computed the weight using W of I, j with the formula Pj plus Qj plus W of I, j minus 1. The cost of 0, 3 is computed with the k values, where k is equal to 1 and we obtain 26, k is equal to 2, we obtain 25, k is equal to 3, we get 33. Out of these 3 values, 25 is the minimum, so we are choosing that particular cost as the cost for C of 0, 3 when k is equal to 2, that is the root node would be 2. Similarly, find out for W of 1, 4. After finding out that one, the last combination would be j minus I is equal to 4. We have only one particular combination for this one where I is equal to 0 and j is equal to 4. Now we are supposed to iterate 4 different k values. K is equal to 1, 2 and 3 and then 4. Using this, we are obtaining the value as 32 to be the minimum search in order to search all the key elements and complete the process. Once after computing all these values, we have to incorporate all these values in the table. This table represents the weight, cost and the root node of the combination j minus I is equal to 0, 1, 2, 3 and 4. The first one represents the combination of j minus I is equal to 0, which includes 0, 0, 1, 1, 2, 2, 3, 3 and 4, 4. Same way for j minus 1, we have computed the combination of it as 0, 1, 1, 2, 2, 3, 3, 4. After incorporating all these values, we are obtaining maximum value as 32 at root node 0, 4 is equal to 2, which depicts in order to perform the entire search, the minimum cost that is calculated for this particular orientation is 32. Now we are supposed to draw the optimal binary search tree for this particular combination. In order to draw the binary search tree, we have the formula Tij, and for calculating the left and the right subtree, we have formula like for the left subtree it is T of k, j, and for right subtree it is T of I, k minus 1. Since we have found out T of 0, 4 is the root node, we are supposed to find out the left and the right subtree. The right subtree, the formula is I, k minus 1, 0, 1, and the left subtree is 2, 4. Using this, we have to proceed with the other iterations and find out the value. Since we have T of 0, 0, 1, 1, 2, 2, 3, 3 and 4, 4 as the values here, and the cost of iterating these trees is 0, we are eliminating these external nodes and keeping these particular values alone. With this, we have the k value as 1, 2, 3 and 4 here, which is already present in the question, and this is the final